So lastly, we're going to talk about cobwebbing. So say I have a system of the form, call it M this time. M is equal to M of t plus 1 is equal to 6 over 10 mt plus 10. Okay, this is just the system that I decided to do here. Okay, and so our updating function for this system, if we care to write it out, and we should, is just the same thing. It's f of x is equal to 6 over 10 x plus 10. And this is exactly what I have drawn here on this graph. This is actually right over here. We have 10. This is our y-intercept. The slope of this graph is 6 over 10. And this is what we have over here, right? On the y-axis, we have our f of x. And on the x-axis, we have our x. This should not come as any surprise. Now, before we go any further, let's go ahead and really quickly compute the equilibrium of this equation here. If we go ahead and calculate x star, we know that this is going to be 10 over 1 minus 6 over 10. This is going to be 10 over 4 over 10, which is going to be 100 divided by 4, which is going to be 25. So our equilibrium, based on a algebraic approach, is 25. So that means if we put 25 into here, we should get 25 back. All right. With that said, let's go ahead and do it graphically. So in order to cobweb, and this is one thing you can do with cobwebbing, is find the equilibrium graphically. All you do is you plot your f of x function, your updating function, and then beside it, you plot x, the function y equals x. So this is just the function y equals x. It's a straight line. It's the easiest function that you've seen, right? And so remember that the equilibrium, in order to find it, we set x star is equal to f of x star, right? This right over here says that whatever we put into our updating function, we get that thing back. That's what it means when we do it this way, when we write it. That's why we write it. But if we were to think about graphically, when I set two functions equal to each other, when I set the function x equal to the function f of x, I'm going to get the intersection point between them. And actually, if you look closely over here where they intersect, which is right over here, okay, they intersect at exactly these points, which is 25. And so it doesn't matter if you, because this is the line y equals x, whether you go this way or that way, you will get 25, okay, as your equilibrium. So the equilibrium in your cobwebbing can be found by looking at the intersection between your y equals x line and your updating function, okay? So this is important. I'm going to write it. The equilibrium is the point of intersection between f of x and x, okay? And because x is the function x, right? Because x is x wherever, so when x is 50, the function x is 50. When x is 100, the function x is 100. It doesn't matter if it's the x or y of the equilibrium point, but that's just for the equilibrium, right? So all that means is that, you know, whether you say it's the, so if this is the equilibrium, it's 25, 25, right, on this graph. It doesn't matter which one you pick of these, if it's the x component or the y component, because they're both the same, because it's the intersection with the function y equals x. But that's besides the point. Point is that the point of intersection between the function x and f of x will give you the equilibrium, and that is helpful. Now, the other thing you can do with this is actually what is referred to as cobwebbing, which is get the solution of this dynamical system graphically. So what I did here is in Excel, I plotted out the values, okay, of this dynamic system that we would get if we were to actually calculate it numerically. But now let's do it graphically. So what I'm going to do is let's assume an initial value, right? So by the way, in this table, this column right over here is my time, and this is MT. Okay, let's assume an initial value, M naught, is equal to 80. Okay, so 80 on our graph, if this is 60, 70, 80, 80 would put us right over here. This is our 80, okay? This is 80. This is where we start. So how do we actually get this value, the next value, right? If our initial value is 80, and that's at t naught, how do we get the value at t equals 1, right? How do we go from m naught to m equals 1? Well, what you could say is, well, we have this convenient function that we have derived of the form r to the t x x naught minus x star plus x star. But this is only valid for a particular case of updating functions, which happens to be the one we're dealing with. But I want to use the more general approach because we'll see that cobwebbing is valid for any kind of functions. You don't have any restriction on what kind of updating function you're dealing with. It'll be valid for any kind of system you want to do. So all this to say that if we want to go from m naught to m1, all we do is we apply the updating function to m naught. So in other words, we take m naught and we put it into the updating function. So what does that look like? We evaluate the updating function at m naught. So let's do that graphically. We're going to take m naught. Okay, we're going to take m naught. Okay, we start at 80 and we are going to go all the way up to our updating function because we are evaluating it. Okay, so we go over here. Why do we go over here, right? Is because we are quite literally, when we are going up to this point, seeing where it lands on the line f of x, the y coordinate over here is quite literally going to give us f of x, in this case, f of 80. Okay, this y coordinate is going to give us f of 80, right? That's why we bother doing this, okay? And if we look at this, well, it's around 60. If we were to actually trace it out in a straight way, it's like 60, it's 58, okay? You can see that pretty well because it's to scale, all right? So this is what we did. We went from 80 all the way to where we hit our updating function, and the y value over here, if we go down and look at the y value right over here, this y value right here, which is approximately 58, gives us the next point, gives us m1. So graphically, this is how we found m1. So now what we can do is we can find m1 on the x-axis. Okay, so m1, the 58, is approximately over here, right? We'll find 58 on the x-axis, which is roughly over here. And the way we can find it more exactly is we use this function y equals x, because what we can actually do, right, is because this function x, whatever's on the y-axis is on the x-axis, meaning that if I put 100 into the function x, I get back 100, right? There's 100 here, 100 here. If I put, 50 in the function x, I get back 50, okay? So what I can do is I can take this 58 and I just bounce it back down over here to get where the 58 is on my x-axis. Now, this sounds kind of confusing. Why am I doing this? It's just a way to get this 58, because what is this 58? This 58 is the value m1. How did we get it? We did it by plugging in 80, putting it into the updating function and seeing what that equals to. That gave us 58, okay? But now, because we want to know what m2 is, right? The idea is to get the next solution. We need to put m2, that is to say, we need to put 58 into the updating function. And so doing the mirroring with the x, like sending it over here to x and then sending it back down, is just a fancy way of getting this 58 on the y-axis to show up on the x-axis. But what we essentially are doing here, okay, is once we hit the 80, we get that our solution to this 80, once we put in the 80 into our updating function, we get the solution is 58. And then all we do is we use the function y equals x to bounce our 58 back on the x-axis. And why do we do that? Is because what we're going to do next, okay, what we're going to do next is we're going to take the 58 and we are going to put it into our updating function. So we're going to take the 58, we're going to put it into our updating function. And then what we're going to do is we are going to see where that lands us. And that lands us at about 45. And reminder, why did we do that? Well, actually, it lands us at 44.8. Because if we take a value on the x-axis here, we feed it into the updating function, which is the blue function, and we see where that lands us over here. This is going to give us the next value, right? Because if we put a value, if we put a number in the updating function, if we put 58 into the updating function, we're going to get as an output what comes after the 58. And what comes after the 58 is the 44.8. That's what comes after the 58, right? And so this is what we get over here. This is exactly what we get over here. We get 44.8. Okay, that is why we do it, right? So we start at M1. The 80 over here was M1. We go all the way to the updating function and we see, oh, the next value, sorry, 80 was M naught, 80 was M naught. We go over here to the updating function, we see that M1 is 58. Okay, then we're gonna put 58 on the x-axis over here. This is M1, it's 58. Okay, then we're gonna bounce it over here and we get that M2 is 44.8. And so what we're then gonna do is we're going to take this 44.8 and put it on the x-axis here. This is our M2, 44.8. And we're going to take this M2 and then we are going to feed it right back into our updating function right here. And then we're going to get our M3, okay? And then we're going to get our M3. Now I drew all these lines on the side here, but in reality, all you're doing is this, okay? You're going straight up to your updating function, and then you are going to the x function, and then you are going to the updating function, and then you're going to the x function, and then you're going to the updating function. And that's how we get all your values, okay? And what you can actually see is if we follow these arrows, we are approaching the equilibrium, okay? We are approaching the equilibrium, and this is how we can predict that the equilibrium is stable, because if we cobweb towards the equilibrium. So let me just recap. Let's do this again. I know this is confusing, so let's do this again, okay? We're gonna delete all these arrows, delete the equilibrium, get rid of all that. None of this is here. And we're gonna start again at 80. 80 is our initial value, right? M naught is our 80. M naught is our 80, okay? We are going to go, we're just gonna put down the y equals x function right over here. And the first thing we're going to do is we're going to take, let's use a bigger arrow. We're going to go from 80 and we're going to evaluate our updating function at 80. That's what we mean. When we go up from 80 over here and we stop at the updating function, that all we're doing is we're putting in the 80 into the updating function and seeing which corresponding y value we get. We're just evaluating it. So anyway, we take 80 and we go over here, and what value do we get? We get exactly 58. 58. This over here is 58. And you can see it graphically, that's 58. Even though it's graphic, it's pretty close. And this right over here, this 58 is the value of M1, okay? We started with M naught, which was 80, and then we got M1. So that puts us over here. Now, let's do this in a lighter color. Now, we want to put M1, okay? We want to put M1 on the x-axis, okay? Because we found M1 on the y-axis, but our goal is to find M2. And in order to find M2, we need to stick M1 back down over here on the x-axis. So what we're going to do is we're just going to go to the x line right over here, because this just helps us mirror it. And we're going to go down over here and we see, oh, okay, this 58 that was M1 over here, well, it's over here. Like if I want to just take this 58 and conveniently just place the 58, but on this axis, I can just go meet this line and then go down. That's why we do it. So this is our M1, okay, which is 58. And then what we're going to do is, well, we want M3, right? Why are we putting in, or sorry, we want M2? Why are we putting in M1 into the step function, into the updating function, right? Why am I evaluating, right? Because when we go up and we meet this, when we intersect with this blue function, all we're basically doing is we are evaluating the updating function at this point or at this point. Why do I want to do that? Because that's going to give me the next point, right? It's going to give me the updated point. So this is why I'm going to take this point over here, the 58, and I'm going to feed it into the updating function. Boom, okay? And this value right over here, this value is going to give me my M2. This value is going to give me my M2. And it's approximately 44.8. See, if you zoom in, this is 40, okay? And so this is like 45 over here, and this exactly would be 44.8 as, that's not a 9, it's a 4, 44.8, okay? As we have over here. That's our M2. Now, if we want M3, this is going to be M3, 36.8 or 36.9. This is M3. How do we get M3? Well, we're going to take M2, okay? And we are going to want to put M2 into the updating function. So how do we do that? Well, we go M2, we go all the way here, right, to the X function, right? Because this X line right here that I just deleted and put back, all it does is it helps us get the M2 from the Y axis all the way to the X axis. So we're just going to go over here, put it here. And now this point right here is our M2, which is at 44.8. 44.8, okay? And then we're going to take that and we are going to plug it into our updating function and see where this lands us. And this actually lands us at M4. And now, if you ignore these lines, and just the way it goes, you'll notice that you always go up from the x-axis to the updating function, okay? Then you go sideways to the x function, and then you go back to the updating function, and then you go sideways to the x function, and then you go back down or up to the updating function. So if you're forgetting how to do this on an exam, what you don't want to do is do this. Go to the x function up and then go to this function this way, right? That is actually wrong. So if you need to remember this, all you do is you go up or down to up / down to the updating function f of x, and you go sideways to the function y equals x. This line over here, this function y equals x. And so this is how you basically cobweb. You get your solutions out graphically. And what you can see is if you keep doing this kind of thing, if you keep going and following these arrows, you're actually going to get to this clever point of 25. And you can start over here too. You can start at 0, and you're still going to get to 25. No matter how and where you start, you're going to finish at 25. And this is precisely why this 25 right here is a stable equilibrium, because no matter where you start, you could start over here. Okay, if I start over here, I'm still going to get there. You don't believe me? Watch this. I start at 100, boom. I started at 100, boom, I go here. Okay, then I go here, then I go here, then I go, oh, and there we go. I fall down this ladder and I'm going down there, okay? I'm going to the equilibrium. So this is the graphical method of solving problems related to systems. And the best part is that this will work for any updating function. Like this equation that we encountered here, this kind, where is it? The C of t, like the general solution, C of t is equal to r to the t x naught minus x star. This only works if our time-dependent system, discrete time-dependent dynamical system, has this kind of form, is written in this way, if the updating function is a straight line. But this thing, the cobwebbing stuff, will work for any updating function, meaning if I give you a plot that looks like this, if I give you a plot that looks like that, this is the updating function, right? So I'm going to draw it. This is the updating function, my updating function f of x. So this is my updating function. And then this right over here will be the function y is equal to x. Whoops. Give me a moment. This is going to be the function y is equal to x. So I did invert the colors here. Let me change that. Might as well keep it consistent. This is going to be my updating function, f of x, and then the blue function can be the yellow function can be my function y equals to x, just for the sake of consistency. Okay, we can see that we have an equilibrium right over here. It's the intersection. Now the question is it a stable equilibrium or is it an unstable equilibrium? Well, let's see. Pick a point. Let's start over here. Where do we go? We go over here, boom. then we hit this guy over here, boom. Then we go to this guy over here, and we go to this guy over here. Oh, we're spiraling towards it. Yep, this guy here is a stable equilibrium. This is a stable equilibrium. So that begs the question, what's an unstable equilibrium look like? Ignore this line for the moment, but I'm just going to put this line over here. And don't pay any particular attention to it, but we'll see why it's important in a second. So let's now say that my function, my updating function, is like this. Okay, this is my updating function. Now let's see if I'm stable or not. So I'm going to start, say, over here. Cobweb, we go over here. Boom, 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 boom. Yeah, we're stable. Okay, so that's a stable one. That was pretty boring and uninteresting. All right. Now, and keep in mind, this function right over here was stable. It went from here to here. Okay, that's the function that we just used. Now let's say I have a different function that goes from here to here, like that. Okay. This guy, if we actually try to cobweb it, first let's pick a point over here. Then we go over here. Boom, we hit this function. And then over here, we would hit, well, if we extend this, we would hit somewhere here. And then we would have to hit the x function again. So we would go ahead and hit somewhere there. And this is going to be clearly unstable, right? Because no matter how close you start, you're going to end up away from it. I'll just recap this. No matter how close you start, you're going to end up away from it. I could start like over here. I could start literally over here. So I'm very close to the equilibrium. I go right over here. I'm super close to the equilibrium, right? Then I go find my line y equals x, and then I go find my line, my updating function, and I'm further away from it and further away from it, right? This is the updating function. So that was unstable. And basically, when you have functions that cross through here and here, this is basically the stable region. Doesn't matter if they go like this or like that. If your function crosses from here to here, this is stable. And if it goes from here to there, it is unstable. Okay, so if we go, so last thing I want to talk about is the semi-stable equilibrium. If you had something, and this is your line y equals x, if you had an updating function, ignore this blue line here for now. If you had an updating function that goes like this, then you start down here, say, you go over here, oh, boom, 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 you are going to your equilibrium, you're stable. But if you start on this side, or say closer over here, I go to f of x, I hit x, and then I'm just going out further. So that's the idea of a semi-stable equilibrium. It's stable only if you get to it from one side. You're not likely to encounter them in your course. Maybe you will, maybe you won't, but they exist. So you should know about them. And you can always determine the stability criteria based on the graph. Now, if this is, I'm going to give you a shortcut your professor might not have given you. So this is the line x, and this blue line that I told you to ignore earlier is just perpendicular to it. If your function, if your updating function goes in these two places, so this is your equilibrium, let's assume it's there. If your updating function goes like this kind of thing, this is a stable region here. This is a stable region. This is a stable region. And this is an unstable region. This is unstable. So let's just, I can illustrate that pretty easily. Let's say I have a function that goes, and again, if it crosses both the regions, so let's say it's something like this, okay, where it goes from, like it's in here and here, then this would actually be semi-stable. If you start off here and you cobweb, you will actually cobweb your way out of it. But if you start off here and you cobweb over here, you will cobweb your way into the equilibrium. So If your function's kind of like this, it's stable and unstable. It depends on the side. If your function's anything that goes like that, or like that, or whatever, like this, it's all going to be stable. And the really steep ones are going to be your unstable. Again, you don't need to memorize this, but this is like the general case. You should always be able to cobweb your way into knowing whether or not the equilibrium is stable. But if not, here's a method. Okay, hope these videos were helpful, and please let me know if you have any questions.